Hello, good evening. Today is October 20th evening, 2021, and I'm recording this placeholder presentation because I give a keynote presentation tomorrow, October 21st, first thing in the morning at 7:30 a.m. Dallas time, 8:30 a.m. New York time, October 21st, 2021 at IEEE SmartWorld. It's a very well-known conference and focuses on smart world, smart things, Internet of Transportation, and so on. I'm very honored to give this presentation. I will, of course, be live tomorrow morning and give the same presentation, but I always record the presentation the night before or a few days prior, because just in case there is a technology glitch. Okay, so what I'm going to do now is I'm going to share my screen. Okay, and let's see, where is this presentation? Right. Okay, so what I usually do is, right, so I'm going to send the link, the Zoom link to the conference organizers as soon as I finish this presentation and get the recording. And again, I'll see you all in the morning. So my talk is integrating cybersecurity and data science, artificial intelligence with applications in smart world systems. Okay, so my talk is going to be in 3 parts. Part 1, integrating cybersecurity and data science / AI. So for this presentation, I'm going to use AI, data science / machine learning, all these words interchangeably, even data mining. So the first part will focus on big data security and privacy, privacy aware quantified self, data science ML AI for cybersecurity applications, securing data science ML AI techniques. So what happens if the machine learning techniques are attacked, and also some aspects of trustworthy machine learning / AI. Then part 2 is security and privacy for smart world systems. And in particular smart world system that I'm going to focus on is the Internet of Transportations and infrastructures. So remember, I talked about smart world earlier, right? Just the previous chart. Smart world could mean many things. So I'll give an introduction to what I think smart world is, and also some quotes from other write-ups on the web, and then talk about a particular aspect of smart world, and that is the Internet of Transportation. And finally, applying part 1 to part 2, which means applications of AI and security for smart world systems, such as Internet of Transportation and infrastructures. So I'm sort of combining a lot of work, right, into this one presentation. So I have to thank several colleagues and sponsors: National Science Foundation, Army Research Office, Air Force Office of Scientific Research, NASA, NIST, NSA, and my colleagues, Professors Alvaro Cardenas, Murat Kantajalu, Latifa Khan, former PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1 is integrating. I'm just keeping an eye on the time. So it's about 7 o'clock. So I'm supposed to finish, I think I have an hour for the presentation. So 45 minutes, and then we'll have questions and answer session. Part 1 is integrating cybersecurity, AI, ML, data science. Okay, so before that, I hope all the sound and everything works in Zoom, because yes, great, because I always get concerned. Okay, so part 1, right? So what I'm going to do is give a motivational example. So I believe I introduced the idea of data mining, security, and privacy. So data mining for security and privacy considerations at a keynote address that I gave, that was back in 1996, 25 years ago, IFIP 11.3, and at the IFIP conference in data and application security, and later in 1998 in Melbourne, Australia. So 1996 was in Como, Italy. 1998 was in Melbourne, Australia. And that was the Pacific Asia Knowledge Discovery Conference. And then I call it a landmark paper that I published because I was a program director at National Science Foundation. And then I published a paper in SICK-ADD. So when you are a program director, of course, when you write a paper, everyone sort of follows that and cites it. Why? Because, you know, you sort of make funding decisions, right? Okay, so then the privacy preserving data mining was coined by the researchers at IBM. Example is Professor Rakesh Agrawal from IBM Almaden Research Center and his colleagues. And so the whole idea is that you have the original data set, and then you add some noise, perturbation, randomization, and then you have the modified data mining process, but the end result should be the same. Otherwise, what's the point in doing data mining, right? So when I joined the university, when I was at the MITRE Corporation, when I was sort of introduced data mining, security, and privacy, then went to NSF. And then when I joined the university, my first PhD student, a lady, Dr. Li Liu, and we co-supervised myself and Dr. Murat Kantajulu between 2005 and 2008. And she focused on privacy preserving decision trees. And data mining, security, and privacy is exacerbated with big data and data science, hosted an NSF workshop on that particular topic on big data, security, and privacy. And that was in September 2014. And then I presented the results to the interagency working group in February 2015. I believe that was about the sort of the early days of big data, security, and privacy. Okay, so what's big data, security, and privacy, right? So technological advances, it's now possible to capture and process lots of data, right? For security tasks, for other tasks. So security tasks, even for authentication, you need to gather a lot of data about a person, a multi-factor authentication to authenticate the person, access control, anomaly detection, monitoring the user, insider threat, and so on. So by analyzing and integrating large amounts of collected data on the web, you can identify connections, relationships among individuals, and that could in turn help with homeland protection, disease outbreaks, especially with COVID-19, right? Lots of applications of machine learning, data mining, and so on, right? And massive amounts of data, collected data, even if anonymized, right? You remove the identifiers, then you can link the records. So even if you anonymize the data, you can link several pieces of data and identify the individual, right? So security tasks such as authentication, access control could require detailed information, as I said. And if this information is misused or stolen, it could lead to privacy breaches. And directions include secure data access, access control models, privacy enhanced techniques, big data analytics for cybersecurity. And there's this whole area called secure machine learning, because what happens if the machine learning techniques are attacked? Okay, so after the project, after the workshop, we had started a project on privacy-aware quantified self. So we are carrying so many devices, right? We don't even realize that just within a day, right? We have our cell phones, our laptops, our iPhones, and our iPads and our desktops and the refrigerators and television. I mean, they're all kinds of gadgets. And now we are using Zoom. So lots of information being collected. And there is this whole area called quantified self that sociologists and psychologists are focusing on. And what does that mean? In this quantified self movement, if information, the whole idea is to collect lots of information about people so that we can give them better advice for healthcare coverage, not healthcare coverage, for improved social health habits and social habits and so on, right? Because wouldn't it be great if I open the refrigerator and I get a warning, because I love milk chocolates and vanilla ice cream. And so I get a warning, say, oh, you shouldn't be eating chocolates, right? So that will be really great because all the information collected about me and then using it for enhancing my life. That is wonderful. However, that can cause serious privacy concerns because what happens, it finds that I'm smoking and give that information to my insurance company. By the way, I do not smoke. So such data collection and sharing without the user's consent, right? And it can be used improperly. So data collected by device monitoring blood glucose levels, it could be used to deny not only insurance coverage for me, but for my son and for my grandchildren, right? So that could be a huge problem. Such privacy violations could easily get out of control if data collectors could aggregate financial and health-related data with tweets, Facebook activity, purchase patterns, and so on. Could result in lawsuits. And so to address these challenges, we urgently need tools. Privacy for quantified self applications. So you can see there is this Fitbits and blood pressure devices. I think it's a glucose monitoring device and so on. Okay, so what we believe is that our cell phone, right, our mobile phone, lots of data, health, fitness, location, social media, image, and other, so on. So you collect all the data, but whenever you collect the data, policies have to govern the data collection. So some of the data could be encrypted in the cloud, some others anonymized in cloud-based services. And now you have this is what we developed, privacy-aware quantified self-manager running on a mobile device. So there's data collection, data storage, data analytics, data sharing. Every step of the way, you need to come up with appropriate policies, right? So realistic policies, that's the challenge. So this is the mobile device, right? Data framework. Some of the data is stored locally, the quantified self data, the mobile app, some of the data in encrypted data storage in the edge or the cloud or whatever. So lots of data being collected, right? It may not be sufficient to store all of the data. Some less frequently accessed data could be stored in the cloud. And so again, based on the policies, local apps running on the device could be given access to some of the collected data. When needed, these apps will be allowed to access some of the encrypted data in the cloud. In some cases, you may not need to collect data every day. A 20-year-old person, you don't have to weigh that person every day, because even if the person increases in weight by, say, 3 or 4 pounds within a day, it's not going to make that much of an impact if the person is reasonably healthy. But for a 70-year-old person, if he or she, even if she's reasonably healthy, but a 3 or 4 pound weight difference in 24 hours could sort of tax the heart. So things are very different, right? So in other cases, data may have to be deleted. That's another challenge. When data is deleted, what does it mean? It's not like our jewelry, right? Our jewelry is stolen, right? So then we know the jewelry is not there, it's gone, but the data is deleted. There could be remnants of the data. Do we really know that the person who we have given the data to has really deleted the data? So that's why we need policies. Policies have to govern the data deletion, data access, data storage, and so on. So when data is deleted, a policy has to say the data is deleted according to policies, so only certain people can delete the data. And then maybe there could be some sort of accountability, right, for deleting the data. So we envision that data sharing and analytics could be carried out as services based on different scenarios. Some of the data could be sent without any modifications, some have to be sanitized, and so on. Okay, so essentially our point is policies have to govern the entire data lifecycle process. Okay, so now we go to the next topic, data science for cybersecurity applications. So the question is, how do you apply data science, right, data mining and so on, for cybersecurity? So using past data to build classification model, right? Predicting the labels for future instances, especially, supervised, unsupervised learning, whatever, using the model, and that helps in decision making. What I'm saying here is nothing new. It has been around for 20 years, right? But the challenge is we are working with data streams. Data is coming in streams like network traffic data, stock market data, like today it is. Anyway, data is coming in streams continuously. As a result, the concepts could change. So today we say by Microsoft, tomorrow by Google, next day by Facebook, the following day by Amazon, and then by, what's the company left? IBM. And Apple and so on, right? So continuous flow of data, but the concepts are changing. It's very common in a digital world, massive amounts of data. So what is our challenge? As these concepts change, one model, what we are doing here, does not fit all. So we are developing an ensemble of models. Models are getting updated. So we have a collection of models, right? And so data is coming in. Benign means we just store it, but if it's attack, testing and training, right? So sorry, training and testing. But the model, after a while, it may not be valid. So what do? We update the model, right, with the new data and so on. So there could be an expert in the loop, but we'd like to do, we do, our algorithm can handle without any expert. Okay, but the expert should check periodically. Okay, so we applied this to a number of applications, wrote a number of books, but our most recent book, which was published around 3.5 years ago, was on insider threat detection. What do we mean by that? Right? There are bad people pretending to be good people inside an organization. Similarly, bad processes pretending to be good processes inside an organization. So insider threat detection requires identification of rare anomalies in contexts where evolving behaviors tend to mask such anomalies. They're pretending to be good. So we have designed and developed ensemble-based stream mining algorithms. You can say stream-based machine learning based on supervised learning, unsupervised learning, and so on. Okay, the result for supervised learning is a classifier, substantially increased classification accuracy. We use traditional support vector machine, one class support vector machine. We've also designed and developed unsupervised ensemble-based algorithm that maintains a compressed dictionary of all the repetitive sequences that people type throughout the dynamic data streams of unbounded length to identify the anomalies. In unsupervised learning, compression-based techniques are used to model common behavior. Okay, so it results in classifier exhibiting a substantial increase in classification accuracy for data streams containing insider threat anomalies. So ensemble-based classifiers allows the unsupervised approach to outperform traditional static learning approaches. So we got some very good results. So here we show a picture. So the person is typing in all kinds of stuff, could be an insider, could be a bad person, could be a good person. So we look at the I chunks, we use the I chunks, extract features, and then what do we mean by that? So we gather the data from, then a new chunk comes in. So gather the data, sorry, extract features, because all the other features have been extracted. Extract the features, and then we develop based on either support vector machine or one class support vector machine or GBAD, the graph-based anomaly detection, the unsupervised. We develop an ensemble of a collection of models. The bad models are thrown away. Bad means the outdated models. Okay, so ensemble based. So it's not one model fits all. Models are changing, and we have to handle those changes. Then the I+1 chunk arrives, and the feature is extracted. We do the testing, and then is it anomaly or not, right? So we test it with a new set of models. And so the bad models or the outdated models are thrown away. So that is the research challenge that we have here. Okay, so we got some good results. Fine. Now comes the sort of most challenging part. I think this is one of the hottest areas in machine learning, cybersecurity and machine learning integrated. What happens is that the machine learning models, what the adversary is trying to do, because see, if the machine learning models are bad, or if the data that we are using to train the models are corrupted, then there is really no point, is there, right? So the machine learning model so we develop the models, and the adversary is trying to defeat our model. So that's called adversary. So we got to understand adversarial learning. What is the adversary trying to learn? It's not concept drift. It's not online learning. Adversaries adapting to avoid being detected during training time, data poisoning, during testing time, modify the features when data mining is deployed. So there's a game being played between us and the adversary. So let's go back. Okay. So this is a support vector machine boundary. The red squares are the bad instances. The blue circles are the good instances. What is the adversary doing? Watching us, trying to corrupt our data or thwart our model, so that he's going to push some of the bad instances, the red, into the below the boundary line. So these instances are going to be shown as good instances, benign, and that's not what we want, right? So that means this is going to be false negatives, but they are really positive, but they're showing us false negatives. Okay, so we have heard about false negatives, false positives a lot these days, right? With COVID, you've got a COVID test, you can have a positive or a negative or a false positive or a false negative. It's sort of similar. Okay, so that's what we don't want. So what do we have to do? So before I tell you our approach, we have to understand what is the attack. It's very challenging, meaning the adversary has a whole range of attacks. So we have only come up with two classes: the free range attack, where the adversary can move the malicious data anywhere in the domain. So it could be between a lower bound and an upper bound. And this is all in our paper. This was one of the early papers that was published in this area. Or a targeted attack, where adversary moves the malicious data closer to the target point. Okay, so adversarial machine learning, we developed adversarial support vector machine to handle the adversary. Our threat model, test time or deployment time, attacker modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. Okay, so what are we doing here? The dash line is the old support vector. That if you didn't do any changes, the boundary line for the support vector machine. The red squares or crosses are the bad instances. The green circles are good instances, right? So what are we trying to do? Okay, what we are trying to do is doing some game theory, mathematical computations, moving this dash line to here. So now we see a blue line. What do we mean by this blue line, right? That means by moving the support vector machine here, some of the bad instances, right, are being caught. Otherwise, the bad instances, the adversary has pushed these bad instances. And so they're going to be false negatives saying it's not bad. But by moving the line, then we have some of the bad instances are being caught. So you could ask the question, okay, so we can move the line right here. Then all the bad instances could be caught. But if we move the line here, all the green instances, good instances, would be shown as bad instances. That means we are going to get false positives. We do not want false positives. We do not want false negatives. So the challenge is, where do we move the line? So the black dash line is a standard support vector machine classification boundary. And the blue line is the adversarial support vector machine classification boundary. And our paper was published in CKDD. This is a very prominent conference. What is our threat model? Test time deployment attacks. Attacker modifies X to X prime. Modify packet length by adding dummy bytes. Add good word to spam email. Add noise to an image. Right? These are the things the adversary is trying to do. So you can see, again, I'm repeating, positive is, red is positive, and these are the attacks, and the green is negative. So by moving this line, quite a few of the attacks are caught, right? And again, you can move the line right here, but that doesn't do us any good because all these green instances will show as bad instances. So again, the challenge is, where do you move the line and how do you move the line? And that's what's in this paper. Okay, so this finishes, I believe. Oh, okay, not that. One more thing I wanted to mention. So this finishes applying data science to cybersecurity, cybersecurity to data science. We also talked about big data, security and privacy, privacy aware quantified self, and then this whole area of trustworthy machine learning, right? So this is one aspect of trustworthy, because if machine learning is attacked, what do you do? Another aspect is, in trustworthy machine learning, computations over big data require massive computational resources, right? Third parties, so you can use a third party survey is used, and then data inherently becomes untrusted. So man in the middle during the data transmission, or insider threat from adversaries, third party location where computation is performed. So we are doing research in secure encrypted data stream processing using the Intel SGS chip, and I'll explain in a minute, using hardware. So let's do a lot of things in hardware, hoping that there may not be as much attacks. But you can't say just because you are doing things in hardware that it's secure, because hardware also could be attacked. Also, here you see formal methods for machine learning include logic. So another interesting direction is use formal methods. Remember, when those of us who have been in cybersecurity for a long time, and I started my career in cybersecurity at Honeywell in 1985 fall, which was 36 years ago. And we were looking at A1, the highest level assurance systems. And then we have to use formal methods to verify the security properties. And so when you have these machine learning algorithms, use formal methods to make sure that the code, the algorithms and the software meet the specifications. That's another way to verify. I'm not saying these approaches the SGX approach or the formal methods is going to work, but we really need to address this problem. And hopefully, right, we need to conduct research and some aspects could work. And so this is the trustworthy analytics Intel platform. So the key points here is that you have the runtime libraries and the wrappers and the encrypted code. The main thing is some of the data analytics, machine learning should be carried out in secure locations or secure, secure locations in the platform, right? There is the SGX enclave memory, and in the secure locations, you carry out the data analytics. That's the whole idea. Okay, so that finishes part one. So let's see how we are doing with time. So what is part two is, right, so I've talked for about 24 minutes. I've got another probably 20 minutes, right? So part two is security and privacy for smart world systems, Internet of and one example we are looking at is Internet of Transportation and critical infrastructures, okay? Okay, so first of all, you've got to ask, and those at this conference, I'm sure they're all experts in smart world. What is smart world? So I looked at for definitions. IGI Global came up with a nice definition. Smart world, and sometimes it's spelled smart space world or smart world, is described as follows. A concept of a digital world that evolves from the definition of ubiquitous computing, right, promotes the ideas of a physical world that is richly and invisibly interwoven, right, with sensors and actuators, displays, computational elements embedded seamlessly in the everyday objects of our lives and connected through a continuous network. So of course, with smart world, right, some smart world includes many aspects. To have a smart world, you of course need smart cities / intelligent. You of course need smart healthcare, right? You need smart homes. I mean, smart, when I was at Honeywell, that was in 1985 to 88, I mean, there was a smart home that was being built, right? And at that time, smart home was like when you come in, the lights come on. When you leave, the lights go off. Sensors, because Honeywell is very well known company, right? But control system, sensors, and so on. So, and then there was also some discussion about intelligent manufacturing. Of course, now we have intelligent transportation, but all based on this concept of Internet of Things. All these things are connected, including Internet of Transportation. So medical things, and maybe even smart world, which will contain, right, not only smart healthcare, maybe smart finance, so many things, right? So that's smart world. Now, I'm not trying to look at security for the entire world. I'm sure there'll be smart universe and who knows, smart galaxy. These are just, I'm just throwing these words, right? So I'm not trying to find the solution for everything, but of course, solving the problem of security and privacy for Internet of Transportation could help us towards achieving our goal, which is to make the world smart. So our research is focused on security and privacy for Internet of Transportation and infrastructures. So Internet of Things, we know our refrigerator is connected to our cell phone, is connected to our, just close this, connected to our cell phone, and is connected to our television, our smartphones, and even the camera here that I'm displaying myself. So again, that's very dangerous. What happened if the camera is attacked, right? So sensors and actuators all over. Whenever there's a microprocessor, right, that could be attacked. So everything is connected, which makes it very dangerous, right? So similarly, in the transportation area, right, all the cars are connected to the trucks, to the trains, and so on. You can have Internet of Things for transportation, ground transportation, air transportation, and transportation by sea and the ocean. Okay, so Internet of Transportation, IoT, Internet of Things, major implications for the transportation, autonomous vehicles, we know AVs, improve day-to-day activities such as delivering packages, improving traffic, and the transportation of goods. In the US, trucks alone carry an estimated 63.3% of freight of goods. AVs are not limited to ground vehicles, but also include aerial and sea vehicles, wide range of applications. Level of automation for AVs range from 0 to 5, right? With current ground vehicles in the market having a potential automation, partial automation of 2, not so good. But aerial vehicles have decent automation, which is 4. Companies have invested heavily or investing. GM spent $728 million in R&D in 2018, $1 billion in 2019, and more expected in 2020 and beyond. And I need to get the numbers for 2020. While there is great potential in AVs and the improvements it can do to the transportation industry, security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay, so very briefly, security for autonomous vehicles. AVs evaluate their environment using a variety of sensors like cameras and GPS, inertial measurement units, LiDAR, radar, ultrasonic sensors. Previous research has shown sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing. So vehicles should verify the veracity of sensor signals before acting upon them. So AVs rely on the sensors to evaluate and interact with their environments. For example, this is sensor-based. Inherited issue sensors are susceptible to GPS spoofing and transduction attacks that manipulate environmental physical signs, visual, sound, magnetic, and so on. And then needed defenses, of course, we can have classic computer security, memory protection, cryptography, authentication, but it does not sort of protect entirely while you need them. But then we are talking about tiny, tiny devices here, right? So due to the real-time constraints, AVs trust, and it's real-time too, trust upon and act upon the sensor data without any form of verification. So these are some of the challenges. And so our approach is, you might think it's very straightforward. I'll tell you why it's not. Physics-based anomaly detection. To build a reference monitor using a physics-based anomaly detection PBAD algorithm for ground and aerial vehicles, the algorithm will consist of 3 parts. Build a model offline of the AV's physical invariants, implement an online tool to monitor expected and observed behavior to detect anomalies, right? So first you build a model offline and then implement an online tool, right? And then you raise an alarm if significant residual difference exists between the execution. So offline pre-processing, online verification, anomaly detection, right? So you might think, so what's the big deal? Okay, so let's see what the big deal is. The challenge is to come up with a model, because we're talking about a cyber physical system. It's not a computer system, right? It's not a database system. It could be a very complex, it's a transportation system. It could be a car, it could be an airplane, it could be a ship, right? So you've got to model. That's why you need the expertise of control systems. So my colleague, Dr. Alvaro Cardenas, is an expert in control systems. So he came up with a model, right? So K is a state, Y is the input sensor measurements, and U is the command to rotors, and you have the X, Y, and Z axis, LX, LY, LZ, moments of inertia. M is the mass of vehicle. So coming up with this model, that's a challenge. So offline pre-processing AVs invariants are calculated using a well-known nonlinear models for aerial and ground vehicles, accelerometer, gyroscope, magnetometer sensor on the XYZ axis for the aerial vehicle, vehicle position and screening for the ground, steering for the ground vehicle. Online, we didn't use fancy machine learning, extended Kalman filter. And these Kalman filter has been around for years, that electrical engineers, control systems engineers have been using it, right? It's used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. The algorithm is divided into 2 sections that predicts and corrects the estimation before it is compared against the sensor data. Anomaly detection, a CUSUM algorithm, that's a statistical based algorithm, is used to detect persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. So we are using extended Kalman filters, we are using the CUSUM algorithm, but again, the type of attack and the model, that is where the research is for this part of our work. And it was presented at Usenix Security. And so it's very interesting, interesting piece of work. Okay, so the physical implementation, we implemented in aerial Intel Ready to Fly RTF zone controller, PX4 flight controller, focused on detecting GPS spoofing. We know what the attacks are for GPS and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope 1.5 seconds, overhead is 5.4%. That is for the aerial. So aerial could be drones as well. For the ground, we built on top of a Taxi Ford Fiesta controller. Again, ROX Kinetic came, focused on detecting visual attacks on the camera. Remember, camera is visual attacks. For GPS, it's the gyroscope attacks. Attacks detected after 0.1 second. Overhead introduces 2.25. Each threshold produces a probability of false alarms approximately 2%. So again, 2% could have been acceptable maybe 10 years ago, but now it's still very high. Okay, so this is the ground. We didn't test it on sea vehicles, right? The ground vehicles are cars and the drones. Okay, so that's the security part. For privacy, beyond the security of individual vehicles, transportation sector could greatly benefit from supporting infrastructure, allows communication between vehicles, motion sensors on lampposts, and surveillance cameras, right? To identify traffic jams, reroute vehicles, increase vehicle safety. So from a user's perspective, there's privacy concerns because concerns could arise from all information needed by such systems that could lead to private information being exposed, such as vehicle identification and driving patterns. So I may not want people to know what sort of driving patterns, my driving patterns or where I'm going, right? But on the other hand, you need to collect information about people because you want to make sure that the cars, there are no accidents, right? So, but we don't want to sort of identify the person that's driving badly, but we need to detect the car being driven badly. So again, how do you protect the privacy of the individual? At the same time, we also need to ensure that there are no accidents and there is minimize accidents and maximize the road safety. So legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies, right? So we are going to come back to this. So this is part 2. Part 3 is application of SecAI for Internet of Transportation and Infrastructures, smart world systems. But I'm focusing on transportation and infrastructures. Okay, so first, data science AI for transportation security. Just like we applied data science for network traffic, how do we apply machine learning to detect security attacks, right? Because we just used our data science machine learning was used for network security, right? Network traffic. And for transportation systems, we use extended Kalman filters. So what do we do here, right? Internet of Transportation are subject to attack like any cyber-physical system, streaming data being collected, right, including autonomous and in the future driverless vehicles. As transportation systems go electric, need energy conservation, threats to the security of such systems could cause massive damage, including accidents, loss of lives, as well as stranded on lonely highways due to attacks on energy management. Data science, machine learning techniques are being applied to analyze the data. So the question is, can stream analytics learning being applied to, say, financial data and telecom data, can they be applied to transportation data, right? And the main question is to understand the nature of the complex transportation data and adapt the stream. So instead of extended Kalman filter, how can you bring the stream? All this data is coming in streams, right? Lots and lots of data, sensor data. So can we adapt the stream analytics that I talked about earlier, ensemble-based models that we are a collection, ensemble models, right? So can we develop a collection of models, right, stream analytics techniques, and apply them on massive amounts of heterogeneous sensor data being collected? So that's the research challenge. Second, adversarial machine learning, right? Again, the Internet of Transportation systems will depend heavily on data science, AI, ML. Right? Because without artificial intelligence, we need that machine learning to detect what? Are there going to be accidents? What about congestion? When the cars communicating with trucks and trains, they have to be coordinated. Otherwise, you can cross the railway tracks and the train can come and crash on you and you are gone, right? And so it'll be nice if you have your smartphone and the train is coming, it's talking to your smartphone, bang, tells you, get away, run. So at least you might have some time, right, to run. And so we need machine learning because we are connected analyzing the algorithms, and then giving us the advice and avoiding the accidents. That's one example. So as driverless cars become more common without a human in the loop, we need even more machine learning. So the adversary will be learning the models used by the vehicles, as well as learn about the data. And then what happens if these algorithms are thwarted, right? The machine learning algorithms are very machine learning algorithms that's going to help us for a transportation. What happens if these machine learning algorithms are thwarted by the adversary? There could be utter chaos, right? Everybody will be crashing into each other. Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms. What's the challenge? What sort of game? Is it zero sum? Is it Bayesian? Is it Stackelberg game? We need to understand the data. That is essential. And research is only just beginning. So we're just beginning research on this topic. So that's adversarial. Number 2, machine learning. Number 3 is privacy. Remember I showed a picture earlier with a smartphone. We have data collection, data storage. Right, we're doing okay. Data analytics, data sharing. Instead now, all of this information is in the car. It could be some sort of a gadget in the car, which could have all of this collection, storage, analytics, and storage access, analytics, and sharing. But the data is not your social media data, or, well, in some areas, there's the whole area called vehicular social media, but I'm not talking about that. It's not your healthcare data and so on. Here we are talking about your radar, GPS cameras, LIDAR, ultrasonic sensors. And of course, some of the data, encrypted data in the cloud or an edge, and anonymized data, encrypted shared data, and query the results. So what we would like to build, and we haven't built it, by the way, privacy-aware, policy-based autonomous vehicle, right? So whenever the data is being collected, policies have to govern. So you can't just randomly collect the data, but you also have to make sure the critical data is collected, because otherwise you can have accidents, right? So we want road safety. And so data collection, data storage, data analytics, and data sharing, all between the cars, between the train and the truck, all according to policies. And this is what we would like to build. Okay, so I've got 2 more charts, right? So the directions for this particular aspect I'm talking about, I've been discussing. Developments in integrating cybersecurity and artificial intelligence, data science, ML exploding. Whether we talk about healthcare or finance or manufacturing or helping with us in our daily lives, whatever, it's exploding. Applications for AI for security, we talked about insider threat detection. We've also done work on intrusion detection, malware analysis, and security for AI, adversarial machine learning. Also developments in privacy-aware healthcare and manage one's life's activities, privacy-aware quantified self, right? So manage all our activities. And so I talked about that, right? How do you collect all the information to help us, right? For our health habits, but at the same time, how do you ensure the privacy, right? At the same time, with the development of Internet of Transportation, including Internet of Transportation and infrastructures, Internet of Things, security and privacy solutions are being developed. They're mainly physics-based solutions. So I talked about physics-based solution where we modeled the system, the cyber physical system, and then what did we do? We used extended Kalman filters as for detecting any vulnerabilities. As driverless cars become a reality, more and more AVs will be used, AI machine learning techniques, because you don't want to be stranded in the middle of a desert, right? So machine learning techniques will have to give you advice. How can we help develop AI solutions for detecting malware AV systems? And how can adversarial machine learning work for AV systems? So I talked about that. Can we develop a privacy-aware policy-based data management framework for Internet of Transportation and infrastructures? That's the car picture I showed. And remember, I talked about trustworthy analytics with Intel chips, SGX platform. Is that possible? Is it possible to perform trustworthy analytics machine learning, right? And what about formal methods, right? Can we bring in formal methods into this picture? Numerous opportunities exist for substantial research and development. So this is going to keep us going for the next 20 years. So lots of opportunities. Now come to the main topic, right? How do we make the world smarter and more secure? we have discussed only a tiny aspect, one aspect of making the world smarter and more secure, and that's securing the Internet of Transportation and infrastructures. Even there, we've got so much to do. We need to make every aspect of the world smarter and more secure, including, go back to my list, smart cities, smart health, smart homes, smart manufacturing, smart transportation, smart Internet of Things, everything. We have to be application specific. One size does not fit all, right? Smart cities, we may need to have, what are their requirements? Smart health, what's their requirement? Intelligent home, what's their requirement? Need to gather requirements for each smart area and develop AI data science-based solutions, right? So we have to gather requirements for each smart area. However, security and privacy have to be integrated with the smart world systems from the outset and not be an afterthought. In many cases, what people do is, oh, they develop the entire system. Oh, what about security? And then what about privacy? It's very hard to put things, incorporate them afterwards. So that is, again, that's a challenge we privacy and security and privacy researchers and developers have, because what companies are really want to get the product out the door. So they don't sort of think they do sort of minimal security privacy, but then there are so many vulnerabilities, right? So as we develop this control, I mean, there's more concept systems, especially with cyber physical systems, there's so much work to be done. Okay, so that finishes my presentation. And I'd like to thank all my colleagues, Professors Alvaro Cardenas, Murat Kantajulu, Latifa Khan, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. And I think timing-wise, it's been good. I was asked to give, I think, my talk for about 45, 50 minutes. And I wanted to make it in 40 minutes, but I think I've used 45 minutes, which is good. And so I'm going to stop sharing. Okay. And again, thank you very much for listening to the presentation. First of all, to the conference organizers for inviting me to give this keynote address. And I learned a lot, by the way, especially I learned quite a bit about smart world, right? Because my research had focused only on the transportation systems aspect, Internet of Things and transportation systems. So I read quite a bit about smart world. So I haven't talked about smart world security per se, because I really need to understand what are some of the requirements of smart world. Of course, smart world means smart cities, smart health, smart manufacturing, and so on. So I think we all, if we all do our part, do a little bit, right? So I'm doing Internet of Transportation, you do smart world, you do smart health, security, and then if you can tie it all together, right? In the end, we need to focus security. You need bottom up as well as top down. Bottom up means each of us work in our areas, but that alone is not sufficient. We need sort of integration. So then look at the big picture and integrate and look at it from top down, right? So both we need. And that's why I said, right? And then smart communities, from smart systems to cities to smart communities, and then of course a smart world, and maybe, as I said, smart universe. In any case, thank you very much for listening to this presentation. I'll be there in the morning and to answer any questions. I'm planning to also give this presentation in the morning. And again, thank you very much and see you in the morning. Thank you.